So kind of the take-home message with all of this is we want to be able to look at an atom in any molecule and determine what its hybridization is, because that tells us about its structure, that tells us about its geometry, its bond angles, and things like that. So we're going to summarize how to look at a molecule and determine the hybridization. We're going to go from sp3 to sp2 to sp. So starting with sp3, an atom with 4 groups attached is sp3 hybridized. So now this begs the question, well, what do we consider a group? Any bond is considered just one group. It doesn't matter if it's a single, a double, or a triple bond. A lone pair is considered one group. One thing to note that's not in this list, positive charges. Positive charges do not count as a group. So now, just to reiterate what we know about sp3 hybridization, that means we have a tetrahedral geometry. And we have 109.5 degree bond angles. And when I'm using the geometry here, I'm talking about the electron group, not necessarily the molecular geometry. And I'll parse that out for you in just a second. Here's the structure of methane. We'll be talking a lot more about three-dimensional structures later in the semester, but remember from general chemistry that if you have these straight lines, that means those groups are in the plane of the page. A wedge means it's coming out towards you, and a dash means the group is going back away from you. So in methane, each of these bonds counts as a group. So we have 1, 2, 3, 4 groups. That is sp3. And methane has a tetrahedral geometry, and the bond angles between the HCH, those are all 109.5 degrees. Now let's look at water. So let's say you're given the structure just like this. One of the first things that I want you to get used to doing is thinking about octets. Now hydrogen is happy with just 2 electrons, but a happy neutral oxygen will have an octet of electrons. Right now, only 4 electrons are shown around it from the 2 bonds. But it needs to have enough lone pairs so it has an octet. So we'll add 5, 6, 7, and 8. And oxygen does have 2 lone pairs of electrons. So now we can count the groups. And we count each bond as a group. There's 1, 2. Each lone pair is a group, 3 and 4. So oxygen has 4 groups. It's sp3. And that means the bond angles are approximately 109.5 degrees. The angle changes a little bit when we're dealing with lone pairs, but that's not something we need to worry about. The other thing is that the oxygen in water does have a tetrahedral geometry. Now you might say, well, wait, I learned in general chemistry that the geometry around the oxygen is bent. And that is true, but the bent is the molecular geometry. But really, bent is just a subclass of the base tetrahedral electron geometry. And the truth is, I really don't see any point for you to know these sub-geometries. We should be able to classify every atom based on just the electron geometry around it, because that gives us the information we need. And that's going to be something that's tetrahedral, trigonal planar, or linear. That's it. Now, if you're asked what type of orbitals the lone pairs reside in, you should be able to answer that. Because as soon as you see sp3, we know that the orbitals that went into the hybridization gave us 4 sp3 hybrid orbitals. That's it. Those are the only orbitals on that oxygen. One sp3 hybrid orbital is making up one of the sigma bonds. One is making up the other sigma bond. The other two, those are where the lone pairs reside. So sometimes you might see water written kind of like this, where the sp3 orbitals are drawn on the oxygen. And we can say each lone pair is in an sp3 orbital. Okay, next, if you have an atom with 3 groups, it's going to be sp2 hybridized. And what we know about sp2 hybridization is that they have trigonal planar geometries and 120-degree bond angles. So let's look at a couple of examples for this. Say you're asked about the hybridization of the carbon that the arrow is pointing to. And you could be asked about the hybridization of any of these carbons. But for this one, what you want to do is look at how many groups are around it. The single bond's a group, the single bond's a group, the double bond is a group. 3 groups is sp2. For this next one, we're going to look at 2 things. One, we're going to determine the hybridization of the indicated atoms. The second, we're going to answer the question, in what orbitals do the oxygen lone pairs reside? So first, let's do the hybridizations. And we'll take the carbon first and look at how many groups are around it. Single bond, a single bond, a double bond. 3 groups, it's sp2. Now let's do the same thing with the oxygen. We have a lone pair, another lone pair, and a double bond. That oxygen has 3 groups. It's sp2. So now in terms of figuring out where the orbitals are, when you think of sp2, what should immediately come to mind are the 4 orbitals you ended up with after the hybridization scheme. So we put 4 orbitals in. The 4 orbitals that come out are 3 sp2 hybrids and a p. So now we want to see how those are used around the oxygen. So I'm just going to redraw the structure here so we have something new to work with. And we should be able to figure out how each of these orbitals are used. So the oxygen uses one of the sp2 orbitals to form its sigma bond to the carbon. It then uses a p orbital to form the second bond, the pi bond. Well, what's left? Left over, we have 2 sp2 orbitals, and we have 2 lone pairs. So one will go in one sp2 orbital, one will go in the other sp2 orbital. An atom with 2 groups around it is sp hybridized. So what does sp mean? We'll have a linear geometry at the atom and a 180-degree bond angle. Okay, here's a few examples to consider. So in this first one, we have the carbon, and we have a single bond and a triple bond. Each of those counts as a group. So this carbon has 2 groups around it. and that means it's sp hybridized. In the second one, now we have a carbon that has a double bond and a double bond, still just two groups. So it's sp hybridized. Finally, we look at this third example, and you see the nitrogen. And when you first look at it, you might think, well, there's just a bond. How do we deal with one group? Well, then it should pop in your mind, oh wait, I need to make sure things have an octet. Does this nitrogen have an octet? No. We have 2, 4, 6 electrons around it. It must also have a lone pair so that it has an octet. Now when we count the groups, 1, 2, 2 groups, that nitrogen is sp hybridized.